In this video, we are going to look at an application of the dot product and calculate the work done in moving an object by an applied force. Work is done when an applied force causes an object to move some distance d. If the force is in the same direction of movement, then work is calculated as the product of your applied force times the displacement, or the distance the object moves. Most times we just write it as W equals FD. There are two different units that we will see. If we're in the SI unit system, then work will have the units of, force in the SI system is measured in the Newton, and distance in the SI system is the meter. So work has units of Newton meters. This also is equivalent to a joule. If we're in the US system of measurement, then the units of work would be, force in the US system is measured as a pound, and then the distance in the US system is the foot. You can write it as a pound foot, or most times people write it as foot pounds. So notice that we have two different units, three different units that you'll commonly see when talking about work. Let's look at an example. Albie Workin exerts a force of 10 newtons to pull her cart a distance of 15 meters. How much work does Albie do on the cart? Well, we have our work is going to be our force of 10 newtons times our distance of 15 meters, and this will give us, I think 10 times 15 is 150, and that would be Newton meters. Or if you'd like to, write it as 150 joules. So what if your applied force is not in the same direction as motion? Then work done can be calculated by a dot product. If a constant force F is applied at an angle theta to move an object along a displacement vector PQ, then the work done by F is given by the dot product of your force vector and your displacement vector, which we recall can be written as the product of their magnitudes times the cosine of the angle between them. The way to think of this formula is the right-hand side is really the product of three scalars, three numbers. And so we can rearrange them to write the magnitude of F and the cosine of theta together times the magnitude of your displacement vector. Written like this, we see this first portion, the magnitude of F cosine of theta, that's going to describe just the horizontal component of our force vector. And so that our product is still the component of that force that's in the same direction times our displacement vector PQ. And so we are still in agreement with our previous definition. We also observe that if the angle between our two vectors were 0, if they were pointing in the same direction, then the cosine of theta would be 1, and we would still have just the product of our two magnitudes from our previous definition. Let's look at an example. Anita Job exerts a force of 10 pounds to pull her wagon a distance of 50 feet over level ground. If the handle of the wagon makes a 30-degree angle with the horizontal, how much work did Anita do in pulling the wagon? Now, to calculate our work, we have the magnitude of our force vector. She's pulling with 10 pounds of force, times our displacement vector PQ, or the magnitude of that displacement vector, the length of it, which we say is 50 feet, times the cosine of the angle between them, which we have is 30 degrees. And remember, the cosine of 30 degrees is square root 3 over 2. And so our product, 10 times 50 would be 500, and 500 times the square root of 3 over 2, the 2's would cancel, and we would get 250 square root of 3 foot-pounds of work is being done by Anita to pull her cart. Well, I hope this was helpful, and I'll see you guys next time.